Hello friends, our next topic is demodulation of vestigial sideband. For the detection of VSB, we use a technique called coherent or synchronous detection. In this, we use a locally generated sinusoidal carrier signal that is applied to the product modulator. It is assumed that the local sinusoidal carrier is in perfect synchronism with the carrier in the modulator that is responsible for the generation of VSB wave, hence called synchronous or coherent detection. The input of product modulator is VSB wave and the output is simply the product of VSB and locally generated carrier, and the output is V function of t. In synchronous detection, the product modulator is followed by the low pass filter. The output of the low pass filter is V0 t that corresponds to the scaled message signal or modulating signal. Now we are going to derive mathematically the output of the synchronous detector that correspond to the scaled message signal. For this, setting the phase phi equals to 0 in the local sinusoidal carrier, the output of the product modulator, that is V function of t, equals to AC dash into st cos 2 pi fct. This equation is in time domain and it represents the product of VSB wave, that is S function of t, and locally generated sinusoidal carrier having phase phi equals to 0. For our simplicity, we take a frequency domain equation. For this, we take a Fourier transform of V function of t, and the frequency version of this equation is capital V function of f equals to AC dash upon 2 within bracket S function of f minus fc plus S function of f plus fc, which is obtained by using a frequency shifting property of Fourier transform. Also, we know that the vestigial sideband equation in frequency domain is capital S function of f equals to AC upon 2 within bracket capital M function of f minus fc plus capital M f plus fc into h function of f. Here hf represents the transfer function of the specially designed sideband shaping filter. Now we substitute equation 2 in equation 1. For this, we have to determine S function of f minus fc and S function of f plus fc by using equation 2. So first we find S function of f minus fc, that is equals to AC upon 2 within bracket M f minus 2fc plus M function of f into h function of f minus fc. Here S function of f is shifted right by carrier frequency, or we simply say that we put f minus fc in place of f in equation 2. And to obtain S function of f plus fc, we simply put f plus fc in place of f in equation 2 and we get AC upon 2 within bracket M function of f plus M f plus 2 fc into h f plus fc. Now from equation 1 and substituting the values of S f minus fc and S f plus fc, we get AC dash upon 4 within bracket M f minus 2 fc plus mf into h f minus fc plus within bracket mf plus m f plus 2 fc into h f plus fc. And after rearrangement, we get a two terms. In the first term, we have within bracket h f minus fc plus h f plus fc having common term m function of f, and this h f minus fc plus h f plus fc is equal to 1 according to the property of the sideband shaping filter within frequency between minus w to w. And the second term corresponds to the higher frequency component having carrier of frequency twice of fc and these are the unwanted terms and can be removed by using low pass filter. So after passing through a low pass filter, we get an output that is V naught T, that is equals to AC dash upon 4 into MT, and this is called a scaled message signal having amplitude AC dash upon 4, and this equation is in time domain.